Hi, I'm Scott Solinger, and my presentation is on the Heartbleed bug. So, what is Heartbleed? First, I'll show a quick video that explains just the very basics of what the Heartbleed bug is, and then I'll reiterate some of the major points made in the video so you have a good understanding of the core of the bug for when I get into more details later on. So,
So maybe you've heard of Heartbleed, but what is it?
Hmm.
Well, every time you go to a website and, for example, fill in your password, the website in your browser has to check if it's correct. To do this, your browser exchanges information with the computers where all the information of the website is stored. Imagine this exchange of information like a conversation between your browser and the computers. To avoid hackers stealing this important information, many websites use a sort of software called OpenSSL to provide an SSL encryption. Basically, SSL translates the important information to gibberish that only your browser and the company computer can understand. It goes something like this. Hey SSL, password is banana. Could you pass it on? Sure, dude. The password is... Got it. Banana it is. Even if a hacker steals the message, he can't read it. So your confidential stuff is safe. Awesome! But during these checkups, there's a second parallel conversation going on, a so-called heartbeat. When your browser is connected with the other computer, he constantly checks if the computer hasn't fallen asleep or something. Because this conversation didn't have any confidential information, it wasn't encrypted. It goes something like this. Hello? Still there? Say a three-letter word cat. Yeah, still there. Cat. Unfortunately, hackers could manipulate this request on the website that uses OpenSSL. Still there? Say 500-letter word cat. Those 497 extra letters could be anything, ranging from useless stuff to super secret passwords. By sending out thousands of requests like this, they gathered a lot of confidential information. Heartbleed! Panic! Well, no. It's fixed now. All you have to do is change your password, and if you have a website, update your OpenSSL. Nice!
So, as the video mentioned, Heartbleed was an exploit in OpenSSL that was used in over 66% of websites on the internet, which is why it was so impactful and essentially affected everybody who used the internet, including businesses. And in essence, how the bug worked was that people could send heartbeat requests and form them in a way where they kind of tricked the recipient to replying with more information than was intended. That information could basically be anything, which means sometimes it would be useless and sometimes it would be very valuable credit card information, passwords, to sensitive accounts like bank accounts, really anything, depending on the website you're using. I'll go into more detail later, but that's overall how the bug worked and why it was so impactful. But before I talk more about Heartbleed, I want to go over an exploit from more in the past to give you some context in terms of how Heartbleed's impact compares to other issues that have been found in the past. The exploit I'll be focusing on is the Morris worm. It was developed in 1988 by Robert Morris, and its intention was to determine the size of the internet by basically spreading itself and seeing how many people it spread itself to, or how many computers. An oversight in its design led it to have a much bigger impact than it was initially expected to. So as I said, it was made to spread itself to figure out the size of the internet. With that in mind, Robert Morris thought if a computer already has the worm, it shouldn't receive it again. That way it isn't, counted multiple times. But he thought if he decided to do that, then people could hear about the worm spreading and say, I don't want that on my computer. I don't want to deal with it. So I'm going to write a process to just say, yes, I already have it, even though I don't, and then it won't be given to me. And then obviously his count would be wrong if people were, if he thought it was on some computers, but that he actually wasn't, they wouldn't be included in the count. So what he did to kind of work around that, he said, so every one time out of 7 that a computer says it already has the worm, it just installs it again anyways. And that was a very crucial mistake, as every 1 in 7 times ended up being much too low, as computers would just be infected over and over and over again until they were completely crippled and unusable. It's estimated the worm infected about 6,000 machines, which was about 10% of the computers at the time. So that might sound like a small number, but it was very significant back then. And this is quite different to Heartbleed, as a lot of those machines were unusable. Whereas Heartbleed, everybody could still use their machines. It was just, they might be losing some sensitive information like credit card data, which would have much more like wide-reaching consequences. But the difference in scale is still impressive at 10% infected by the Morse worm to about 66% of computers vulnerable to the Heartbleed. That's a huge difference in scale to give you some perspective on how they differed. And similar to Heartbleed, it wasn't some extremely complicated, nuanced exploit that only true experts could make use of. It was just a simple mistake on the part of Robert Morris in terms of just having it reinstall 1 out of 7 times, even if you already said yes, that really caused all the issues. And then so how did Heartbleed work? As I said before, and as was stated in the video, Heartbleed was an exploit for OpenSSL. It compromised normally encrypted data. Like the video said, the attacker would make a deceptive heartbeat request, an example of which would be along the lines of, hey, if you're still active, reply saying cat, and by the way, cat's 500 bytes. And obviously cat is not 500 bytes. So they would reply saying cat, and then all of the leftover bytes, let's say it took up 3 bytes, then you would have 497 bytes of data that was stored near the SSL v3 records that would be then returned to whoever made that request, because it was anticipating that it would overwrite all of that data with the actual payload, assuming it was the correct size. So that was kind of the main issue. And then, similar to what I said about the Morse worm, it wasn't an extremely complicated exploit that required, a complete mastering of programming and how networks work in order to, use it as an exploit. It was just a very simple programming mistake that was just fairly easy to exploit, and it went undetected for over 2 years, even though the code was available for everybody to see, as OpenSSL is an open source software, so anybody can just go view the code if they want to. Even to this day, you can see kind of where the bug used to be and how they fixed it. And then so what was the impact of Heartbleed? As I said many times before, over 66% of the internet used OpenSSL. So that's roughly the amount of websites that were vulnerable. And exploiting the Heartbleed bug didn't leave any sort of record unless you made something specifically to detect it. And since nobody knew about the bug for a while, those weren't in place. So it's impossible to say every single website that was actually affected, and what data was stolen, and what monetary impact that might have had. But major websites such as Yahoo and IMGUR were still vulnerable when the bug disclosed, and even larger websites like Facebook and Gmail were vulnerable at some time before the bug's public disclosure. So if somebody knew about the bug before it was disclosed and they didn't tell anybody because they wanted to use it for malicious reasons, there's a chance they could have gone after some of those bigger websites and that their data could have been compromised. But there's no evidence to suggest that that was the case. It's just a possibility, really. And then a fix was quite simple. As I said before, the exploit was based on a very simple coding error. Most companies have fixed the issue by this point by just updating their systems. But that still costs money to do, and any certificates they might have had that were compromised also had to be reissued. And any companies who didn't get new certificates, if their secret keys were discovered while the bug was still active, then their data is still completely at risk, as, with the secret key, they can just read all of their communications, even if they're encrypted. And then so what could have been done to prevent this, and what can be done moving forward to ensure that something like this doesn't happen again. Some simple provisions can go a really long way. In the case of the Morse worm, something just as simple as, before releasing it out into the wild, run on a simulator first to see how it might go. He would have figured out the issue very quickly. And that's a bit outdated. Things are tested and simulated now. But in the case of Heartbleed, just having more unit and integration tests can help ensure against just kind of common issues that those tests are really designed for. And the issue in terms of coding away to prevent the payload and the specified size of the payload from not matching up, that's a fairly common programming practice. So there's a good chance that if they, really made every single unit and integration test that they could think of, that would be included in those. Another step is to rewrite current technologies in languages that might be more appropriate to what they're meant to do. C is an old powerhouse of a language that tons of stuff is written on, but writing C that's safe can be difficult, and OpenSSL is currently written in C, so if it were rewritten in a different language that's easier to ensure secure, that could alleviate some of the risks, and the same could be said for other technologies. And then a pretty straightforward step generally is just to pay for security audits. That's something most companies do for their in-house technologies already, but it becomes kind of complicated when it's an open source project like OpenSSL, as they don't really have an organizational structure with a large budget to pay for something like that, even though it's so widely used. Those type of projects typically rely on donations from individuals or large donations from companies who then get to say, hey, we support this technology. But usually that money goes to paying the developers who work on the project, often for free or very little money. So it's just kind of nice to actually get something for their work. So, maybe they need to say, okay, well, we're not going to get paid, or we're going to get paid less, and we're going to pay for the security audit. But also companies could band together and say, hey, we'll contribute some money towards this technology that even though we don't make it, we still use it, and we recognize how important it is and that we need to make sure it's secure. Otherwise, we will lose money as companies. But, then some companies might have an issue. Well, this other company's using it and they're not paying for it. They're not paying for the security audit. So, why should we be paying for the security audit? And it can get a little dicey. But hopefully, after Heartbleed, companies will see just how big of an impact something like that can have. And they'll just kind of bite the bullet and pay for at least, part of a security audit if it could really save them a lot of money in the long run. And so in conclusion, Heartbleed was an exploit in OpenSSL, which over 66% of websites used. It allowed attackers to form an improper heartbeat request and view up to 64 kilobytes of data that was supposed to be encrypted. It might not have crippled computers and systems like the Morse worm did, but it affected a large portion of the websites on the internet and basically everybody who used the internet, rather than only 10% of the computers on the internet at the time, which the Morse worm affected. And the bug itself was a very simple coding error. It could have been prevented with more rigorous tests and perhaps a security audit. And hopefully companies will look back at this issue and do more to ensure proper steps are taken to ensure technology security, even if it is open source and not something they themselves kind of create and own. And then these are my references, and that's it. Thank you.